Okay, so we've talked about some applications of exponential logarithmic functions, and I'm going to just work through some examples just to show you how you solve them. So first thing we're going to do is I think an exponential growth problem. And remember the exponential growth, and I'm gonna use this form p of t. I'm gonna use t as the variable just because a lot of times time is the variable, and p is going to be just the amount of something. So there'll be some initial amount p0 e to the minus I'm trying to decide, well, I'll use at. So t is the variable, and typically you're given two pieces of information, something in some initial amount and some amount after a given amount of time. So let's say given the initial quantity is 50 some units, and the quantity at 2 days, so days will be, the time will be in days, is 75. Determine P0 and A. And then what is the predicted quantity at 4 days? Okay, so we need to determine P0 and A, and to do that, to do P0, we use the initial quantity. So what we can say is that P of t equals 0, or P of 0 equals 50. So what you can do is you can say, so P of 0 equals 50 equals P0 e to the minus a times 0. So t is the variable and the time is 0. So what you get is P0 e to the 0. So it doesn't matter what a is. You're going to still multiply it by 0, so it's going to be 0. E to the 0 is 1. So what we get is P0 is 50. So that was pretty easy. So now we can say P of t is going to be 50 e to the, and actually it should be plus at, not minus at. So let's make that positive because it's exponential growth. E to the at, and you can see it's growing because it's more than it started out as. Okay, so the second thing we do is we use this quantity at this particular time to figure out what a is, and this is where we're going to use our techniques for solving exponential equations. This one was pretty trivial. So what we say is P of 2 days, is 75. So that's the left-hand side of the equation. On the right-hand side of the equation, we have 50 e to the a times 2, or 50 e to the 2a. So we just need to solve for a now. So we got this is equal to that. So we're going to divide both sides by 50. So you get 50 over 70. 75 over 50 is equal to e to the 2a. That's 1.5 is equal to e to the 2a. Now to be able to solve for a, we take the natural log of both sides. Natural log of 1.5 equals the natural log of e to the 2a. So the inverse properties of logarithms and exponentials say that the natural log of e to something is just that something. So we get 2a over here. And the natural log of 1.5 is 0.4054, 0.405. So a is equal to 0.405 divided by 2 So we get 0.2027. So the function, given these 2 points, and assuming it has an exponential relationship, is going to be 50 e to the 0.2027 times t. So it's p0 e to the at. So that was, let me fix that because that's positive. Okay. So now once you have the equation, we can predict it. We can predict it at times between 0 and 2, or we can kind of what we would say is extrapolate. So it's values of t that are outside of the ones that we specified. So p of t equals 4, or p of 4, is going to be 50 e to the 0.207 2.2027 t, and and we plug in for t, we plug in 4. So it's going to be 4, and it should, what should it be? Well, it should be more than 75, because 2 days it's 75, and 4 days should be more because it's continuing to increase. So if we get some number less than what we got previously, 75, then we know we've done something wrong. So you get 50 times e to the 0.2027 times 4, and you get 112. So p of 4 equals 112.4, and that's your answer. So in review, we're given the initial quantity, the quantity after 2 days. You can use the initial quantity to find P0. You can use the quantity after 2 days to find A. Once you have that, you've got the equation specified, and then you can evaluate the function at any value t. Okay, let's look at exponential decay. So exponential decay, let's call it C. C of t is C0 e to the minus, and let's use b just to be different, b minus bt. So b is going to be a positive quantity, but you're going to then multiply by a negative sign. So that this is going to have something that looks kind of like that behavior, where this is c and this is t. So probably the easiest situation is where you're given an initial quantity. So we'll say c at t equals 0 equals c at t equals 0, c equals 0.4. I'm going to put units, grams. And c at t equals 10 years is 0.03 grams. Okay. So from those two pieces of information, we can find C0 and B again. So C of t equals 0 equals C of 0, which equals C0 e to the minus b times t, which is 0. And C of 0 is 0.4 grams. And you get C0 times e to the 0, so C0 equals 0.4 grams. So the function C of t is now 0.4 grams e to the minus bt. So to find b, we need to use the second piece of information. So c of t equals 10 equals c of 10 is equal to 0.03 grams, and that is equal to 0.4 grams e to the minus b times 10. So we're going, if we divide both sides by 0.4 grams, like that, e to the minus 10b. So negative b times 10 is negative 10b. So let's take 0.03 divided by 0.4. So that's 0.075. The grams cancel out, which is good because E doesn't have any units. And e to the minus 10b. Now, I think speaking of units, 10 has units of years, which I didn't put in here. So b would have units of 1 over years, because the exponent always has to be unitless to be exact here. So since I'm dealing with units today on this particular example, so let's go ahead and stick in years here. So it's negative 10 years times b. Okay, so you take the natural log of both sides. Natural log of e to the minus 10 years times b. So the natural log of 0.075 is going to be a negative number. So you get negative 2.5903 equals negative 10 years times b. So b is equal to negative 2.5903 divided by negative 10 years. So b is equal to 0.25903 1 over years. So that when you multiply b times t, you get the units cancel out. So our final equation here is that c of t is equal to 0.4 grams e to the minus 10 years, minus b. So it's going to be e to the minus b. b is 0.25903 1 over years times t. So that's my general expression. Now I didn't ask it earlier, but let's say I want to know what it is after 5 years. So what is c at t equals 5 years? It's halfway. So it should be between 0.4 and whatever it was, 0.4 and 0.03, somewhere between there. It's not going to be linear or average because it's not a linear function. So what we can do is we can do c of t. C of t when t equals 5 equals c of 5, which is 0.4 grams e to the minus 0.25903 1 over years times t, which is 5 years. So c of 5 is going to be 0.4 grams e, and if we multiply this out, so we'll take 0.259 times negative 10, negative 5, is negative 1.2951. 0.5 equals 0.10954 grams, which is between 0.4 and 0.03. Okay, now sometimes you're given, with radioactive decay, you're given what's called a half-life. And a half-life is the time where, let's say, C of t equals 0.5 times the initial amount. So that's why it's called half-life. It's because it has half the amount that you originally started with. So what you can do is you can say C of t equals half-life divided by C0 equals 0.5. So if you take the ratio of the amount at the time where it has half the amount to the original amount, that time is called a half-life, and that's equal to e to the minus bt. So you might be given something like that. So let's say we have a radioactive material with half-life of 1,010 years. If the initial quantity is 4.0 grams, how much is remaining after 2,567 years? Question mark. Well, it's going to be less than half, because 1,000 years you have half, and it's radioactive decay, it's going to be less than half. So you can do two things. You can use the initial quantity to find C0, because what we have is, C of t is C0 e to the minus bt. So C of 0 equals 4 grams. And that equals C0 e to the minus bt, where t is 0. So this just becomes C0 times 1, e to the 0. So just like before, C0 is just the initial quantity. And before, we used the quantity at a particular time to calculate B, but what we do here is we say that C at t equals half-life divided by C0, which is 0.5, is equal to e to the minus b times the actual half-life in years. So we just skip one division, really. So you take the natural log of both sides, natural log of e to the minus 1010 times b. The natural log of 0.5 is negative 0.693. 15. The natural log of e to that is just the quantity. So if you solve for b, it's going to be negative 0.69315 divided by negative 1,100 divided by, and you get 6.8628 times 10 to the minus 4. The units are 1 over years again, since I have these in years. So I should have put years up here. Years, years. So years down there. So the units are 1 over years. So now I can say that the quantity at any particular time is going to be the initial quantity, 4 grams, e to the minus, so it's the negative here, minus b, which is 6.8628 times 10 to the minus 4, 1 over years, times t. So that's my function. And then all I have to do is plug in t equals 2,567. So 2,567 years. So that's 4, and if I got the grams, let me put that in there. 4 grams. E to the minus 6.8628 times 10 to the minus 4, units 1 over years, times 2,567 years. You can see the years cancel out, so that the exponent has no units. So now we just plug it in. 4 times e to the minus 6.8628 times 10 to the minus 4 times 2,567, and I get 0.6, and again, oh, there are my grams, I got it in there. 0.6, yeah, didn't write enough decimal points down. 0.68702 grams. And again, it makes sense because, you know, we said at 1,010 years that the quantity was half the original amount, which was 2 grams. So at 2,567 years, it should be even less, which it is. And really, you can we could say at t equals 2,020 years, we could say c equals 2 grams, or 1 gram, sorry. Is that right? 1 gram, yeah. Because at t equals half-life, c is equal to 2 grams. That's because the initial quantity was 4, so after 1,010 we have 2 grams. After 2020 we have 1 gram at 3 times. So if at 3,030 years we should have C should be equal to 0.5 grams. And you can see that that makes sense too, because this 2,567 is between 2,000 and 3,000, and this quantity here is between 1 and 0.5. Now there are other variations. You know, I could give I could not give the initial quantity, but I could give the quantity at a particular time and the half-life, and I could figure out C0 from that. So those are examples of exponential growth and exponential decay.